Hello everyone, welcome to this video presentation on signals and asynchronous events in Linux. This video was prepared for Embedded Systems Programming class at Arizona State University in fall 2014. The contents of this video will be objective, followed by an overview of an inter-process communication systems, signals, asynchronous events, and asynchronous transfer of control using set jump and long jump. The objectives are to use Linux signal handling mechanism set jump, long jump to demonstrate an example of imprecise computation programming, and to test Linux signal delivery mechanism using trace command and kernel shard, and also to deliver signals to all the threads that are registered to receive a signal. Coming to interprocess communication, also known as IPCs, these are mechanisms that provide communication between two processes. The communication can involve transfer of data or a simple message without any data involved. The communication can happen between two processes that are running in the same host machine, or also between two processes that are running in completely different machines, like a client-server model. And these are the inter-process communication techniques that are available in Linux. The first one is a simple file-based IPC, wherein one process writes some data into a file, and another process can read from a file. Pipes is also similar to file, but it is more advanced in that it uses a FIFO mechanism, wherein a process writes data through one end of the pipe and another process reads it to the other end. Sockets are used for communication between two processes over a network using TCP or UDP protocols. It can also be used to communicate between processes on the same host machine using the local loopback interface. Message queues and shared messages are used for communication between processes running on the same host, and semaphores are used for synchronization and signals of communication using asynchronous events. Signals are triggered as a response to some external condition or action. It is just a notification and does not involve any data. They can be treated as software interrupts. Signals can occur either synchronously or asynchronously. When signals occur synchronously, they are also called as traps, and they occur during the execution of a program, like illegal instruction execution such as divide by zero, or illegal memory access, like accessing an array with a incorrect index. When asynchronous signals are also called interrupts, they occur after context and can be sent from user space to user space or from the kernel space to the user space. When a signal is delivered, it can either be ignored, can be blocked, or it can be handled. But there are some signals that cannot be blocked, ignored, or handled, like sig kill and sig stop. These are signals that are delivered by the kernel to user space process to terminate the process. When a signal is ignored, its delivery will not have any effect. When a signal that is blocked is delivered, it will be kept pending in a queue until it is unblocked or ignored by the process. The signal library function is used for signal handling. It takes two arguments, sig and func. One is an integer, which is the signal to be handled. The other is a function pointer, which is the function that will be invoked when the signal is received. To ignore a signal, we set the function pointer sig ign, and to reset the default behavior for a signal, we set it to sig default. The signal library function is not recommended in a multi-threaded environment as its behavior is not defined. A more robust interface called sig action can be used instead of signal when a multi-threaded environment is used. The sig action function takes three arguments. The first one is an integer. The other two are of the type struct sig action. The first is a signal that is to be handled. The second argument is a new action that is to be installed for the signal, and the third argument is the action that was previously installed for the signal. The sig action structure contains three function pointers and a signal mask and the flags. SA handler is the action that is to be associated with signal. It is nothing but the function pointer or the function that is to be invoked when the signal is delivered. It can be set to sig default for default action or sig IGN for to ignore the signal. The mask contains all the masks of signals which should be blocked. The mask can be set using sig empty set, which will mask all the signals, sig fill set, which will unmask all the signals. Sig add set is used to mask just one signal, and sig delete set is used to unmask a signal. The flags are used to modify the behavior of a signal delivery. For instance, if the flag is set to SA underscore no differ, it will prevent the signal from being received from its own signal handler. Next, asynchronous events are events that arrive at unpredictable times, such as connection requests from a client to a server, or keyboard or mouse inputs. The events can be received using polling or interrupts. Polling is an inefficient method and it has a lot of CPU overhead. While interrupts are efficient and do not have any overhead, they should be handled with care. The input events in Linux are available to event handlers like mousedev, keyboarddev, joydev, and evdev. Mousedev, keyboarddev, and joydev are very specific event handlers for the mouse, keyboard, and joysticks respectively. evdev is a generic event handler available for all input devices. The events can be received through the dev input event files, and the handler mappings are available in proc-bus input devices file. When an event file is read, the information is available in the format struct input event, and this structure contains 4 variables. The first one is the timestamp or the event that occurred. The other one is the type of the event, which is a button click or a keyboard click. The other one is the code, which indicates whether it is the right button or the left button. And the last one is the value, which is if it is 1, it means the button was pressed, and if it is 0, it means the button is released. Asynchronous transfer control in Linux is achieved using two library functions called setjump and longjump. Setjump is used to save the current context, and it takes just one argument, which is of the type jump underscore bub. And this structure definition varies across architectures. On a typical 32-bit x86 machine, this structure saves the base register, the stack pointer, the source index, base pointer, destination index, and the instruction pointer. To restore the previously saved context, we use the long jump function. It takes two arguments. One is the env, which is nothing but the context that was saved earlier, and the other one is the value, which is the return value when making a long jump to a previously saved context. There are other variants to set jump and long jump, such as sig set jump and sig long jump. These are similar to set jump and long jump, except that they can also save the signal mask of the process at that context. Care should be taken not to make a long jump from one thread to a context that is saved for another thread. This will lead to an inconsistent state in the processes and will lead to a segmentation fault, and the process will be core dumped. Now let us see how the various objectives have been implemented through code. The first objective is to demonstrate an imprecise computation pattern by terminating a computation when a signal is received. So the first step is to install a signal handler for the signal that is generated. We use the signal library function that was described earlier, and the signal that is generated is the sig user1, which is a user defined signal, and the function that is installed is the sig handler, which has been defined here. And the next step is to create a thread. This thread essentially reads the mouse inputs and detects a double click. And when a double click is detected, it will send the sig user1 to the process. And the next step is to save the current context using setjump. If the return value of the setjump is 0, which means the current context was saved, and then we proceed with the computation where a simple integer variable called count is incremented every 50 milliseconds. If the return value is non-zero, It indicates that the set jump returned from a long jump using the saved context. And then we print that the computation is being terminated and the final value of the count. Now this context variable is defined globally and it is of the type jmp underscore buf. And next, the mouse thread. The mouse thread opens the mouse event file that is defined by this macro. After opening the mouse event file, we keep reading for the mouse inputs. This mouse input is available in the format struct input event, which was described earlier. And this input event structure provides us with the type of the event, which in this case is going to be a key event, and the code. And since we are going to detect a right click, it is going to be button underscore right, and the value is 0, which means the button is released. For detecting the double click, we use the time variable, and we essentially find the difference or the time gap between two right button clicks. And if this time gap is less than 1 second, which is essentially the resolution that is provided by the diff time function, so if it is less than or equal to 1 second, then we can understand that it is a right double click that was generated, and we print that the double click was detected, and we'll send the sig user1 to the process using the kill function. Get PID will return the PID of the function, and this is the signal that we are sending. Now when this function is called, this signal is sent to the calling process. You can also see that this thread has all the signal blocked, because when the sig user1 is sent to the process, it can either be delivered to the main thread or to its child thread. But since we are going to do a long jump to the main thread, it is essential that we block all the signals for the mouse thread so that the context switch does not happen from the child thread to the main thread. So in the signal handler, it receives one argument, which is a signal that was delivered. So we check if the signal that was delivered is sig user1, and we use a print to indicate that the signal was received, and do a long jump to the context that was saved. The one is the return value that will be returned here. So since it is non-zero, we'll say that we'll terminate the increment operation that was executing in the background, and we print the final count value. Let us see the working of this program. So we have the file here. Let us clean the build and do a fresh build, and let us run the program. You can see that I'm running this as a super user because the mouse event file that is available can only be read by a super user. So when I run this program, a thread is started to detect mouse clicks. When I do the left button click, it does not read any event, but when I do a right button click, the event is read and the double click is detected, and the sig user1 signal is generated, and the increment operation is stopped. Let us look at the other objective, which is to see how the signal delivery mechanism works in Linux. Ideally in Linux, when there are many threads running within a process that are registered to receive a signal, then kernel chooses one arbitrary thread and delivers the signal to that thread. So to demonstrate this, we have program where we start 5 threads, child 1, child 2, 3, 4 and 5. Now in child 1 and child 2 we have all the signals blocked. This is thread 1 function is the child 1, thread 2 function is the child 2, and all the threads, all the signals are blocked to this thread using the pthread sigmask, all the defined signals, while the thread functions 3, 4 and 5 do not have any signals blocked. After starting the threads, the signals are blocked even for the main thread, so that when a signal is received, it is either delivered to the threads 3, 4 or 5. The signal that we are going to generate is a SIG-IO, which is an asynchronous notification, and this signal is generated using a FIFO file. So first we create a FIFO file in the temp folder, and then we set the current process as the owner for the FIFO file, and we also register for the asynchronous events from the FIFO file. As you can see, there is another writer thread. What this thread essentially does is that it writes data into the FIFO file. When this thread is started, it sleeps for 5 seconds, which is defined by this macro deliver time. Now after sleeping for 5 seconds, it writes some arbitrary data into the FIFO file, which will in turn trigger the SIG-IO signal. Since the main thread has all the signals blocked and the child threads 1 and 2 also have the signals blocked, when the SIG-IO function is delivered, it will be either delivered to the thread 3, 4 or 5. So to identify which thread the signal was delivered to, we check the context under which the signal handler is running using the pthread equal function. So in this function, we check the current context with the context of the threads that were started. So if it is child 1, we can see that the SIG-IO is delivered to thread 1. If it is 2, it is going to be thread 2, but essentially these cannot happen as these two threads have the signal blocked. If the signal is delivered to child 3, 4 or 5, the respective print statements are printed. If it is not all this, it is going to be a main thread, which also cannot happen. Now on receiving the thread signal, we simply print and will exit the program. Let us see the working of this program. So let's clean the build, make a fresh build and run the demonstration program. So here you can see that for the 5 seconds all the threads are running. After 5 seconds, well in this case it is 10 seconds, so after 10 seconds when the writer threads write some data into the FIFO, this will trigger the SIG-IO. This writing to FIFO comes from the writer thread. Writing to FIFO. So when this write happens to the FIFO file, it will generate the SIG-IO, and you can see that the SIG-IO was delivered to thread 3, which is here. So from this it can be understood that when multiple threads have registered to receive a signal, the signal is delivered only to one thread. So the other objective is to deliver a single signal to all the threads that are registered to receive the signal. So for this, 3 library functions have been developed. The first one is to register the thread for a signal, the other one is to unregister the thread for the signal, and the last one is to deliver the signal. So essentially for this library, we have a header file, So in this header file, a new structure of the type pthread underscore signal is defined. This structure contains a pthread variable and the signal, the parent of the pthread, and a pointer to the next. This is essentially a linked list, and it is used to keep track of all the threads that are registering to receive a signal. So in the register function, we take three arguments. One is the pthread ID, the other one is the signal that the thread is registering for, and the parent process of this thread. So when this function is invoked, we add this data into the linked list, which is of the type pthread underscore signal, and the name is thread list head. This is a simple linked list operation where a new node is inserted at the beginning of the linked list. And the other function is to unregister the thread. This function should be called by the thread after it receives a signal. So this takes just two arguments, the thread and the parent ID. So in this function, we remove the entry for the thread that received the signal. That is, we delete the entry from the linked list. And the last function is to deliver the signal. This deliver signal function takes two arguments, signal and parent. So in this function, we essentially try to identify the threads that have the parent indicated by this variable and are registered for this signal. So we iteratively check for all the threads that have registered, and we send the signal to this thread using the pthread underscore kill function. Let us see how this library function has been implemented in a demo program. So this demo program is similar to the one that we saw earlier. It has 5 child process where child 1 and child 2 have the signals blocked, and child 3, 4, 5 will register for the signal, and there's a writer thread that is used to generate the SIG.io function by writing to the FIFO file. So after creating the threads, we call the first library function, which is register for the thread. We'll send three arguments, the child, the signal that the thread wants to receive, and its parent ID, and we'll do it for all the three threads that are registering for the signal. Now, once the signal is received in the signal handler, we check the context of the signal of the thread that received the signal, and then we unregister the thread for the signal by using pthread self and the PID. After removing its entry from the linked list, we then deliver the signal to the other threads that have registered for that signal. So this way, if the signal is first delivered to child 3, we remove the entry for the child 3 using the unregister function, and then when we call deliver signal function, it iteratively check the linked list for the other threads that have registered for the signal, and then deliver signal to that thread. And this happens for all the three threads, 3, 4 and 5. Let us see how this works. You can observe that the writer threads does only a single write, which will trigger only one SIG.io function, and we'll see that the signal is delivered to all the three threads which are registered for the signal. So this is the program. This program is gonna run for some time, after which all the threads ran for 5 seconds, and after which the writer thread wrote some data into the FIFO file, which triggered the SIG.io signal, And in the earlier program, we observed that the signal was delivered only to thread 3. But using this library function, the signal was delivered to all the 3 threads that registered for the signal using the register function. Threads 3, 4 and 5 are the threads that received for the signal, that registered for the signal, and that signal was delivered to all the threads that received it. Now let us look how trace command and kernel char can be used to identify the instant at which the signal is delivered to a process. So let us consider an example where we have 2 threads and a signal is delivered from one thread to the other. So in this case, we have 2 threads, thread 1 and thread 2. Both these threads are started as real-time threads. The scheduling policy has get FIFO, and the thread 1 has a low priority of 10 and thread 2 has a relatively higher priority of 20. The low priority thread is started first and then followed by the high priority thread. So these threads do nothing but simply increment a variable in the low priority thread, and the high priority thread will send the signal to the thread 1, which is the low priority thread. When the signal is received, we check the context and ensure that the signal was received to the thread 1 only, and simply do a print to indicate that the signal has been received. So we'll first build the file, and this is main5_2b. So we have main5_2b. To record the events, we run the trace command, record -e switch is used to indicate the events. We are going to record all the events and we are going to output the recorded events into, say, a sample.dat file, and then we're going to be running a program. So now a program has run. You can see that initially the low priority thread which was started was running, and it incremented the variable counter, and after some time the high priority thread with the print thread high running was started, which can be seen here. The low priority thread is running, and after some time the high priority thread came into the picture, and the high priority thread sent the signal. So when the signal was received by the low priority thread, we do a thread exit, and the main thread we do a thread join for the low priority thread. So when the low priority thread exits, we simply print the counter value and exit the program. Now we have all the recorded events in sample.dat file. Let us see the data using kernel shark. So in kernel shark, we can observe that a lot of events have been recorded, but we are not interested in all the events across that have been recorded for the entire system. So we're going to filter out. First we'll select our program. You can observe that there are 3 instances for the program. The first one is the main thread, the other 2 are the child threads that have been started by the main thread. And then we'll filter the graph events. We are not interested in all the events. We'll just display the signal events, and we'll do the same for the list that is available here. Uncheck all and check just signal. So this will remove all other events and just display the signal events. Now this output, you can observe that first the main thread was started here, and the main thread, as soon as we create the child thread, which is a real-time thread, it start executing for some time, and you can still see that the main thread, which is runnable for all this period by this red hollow box, and the low priority thread runs for some time, and then it is preempted by the kernel, and the kernel also executes other processes which have been pending for quite some time now. And in between you can see that there's a small spike here which indicates that the main thread run here. So now this main thread then starts the high priority thread, which is indicated by this green hollow box. So you can see when the signal was generated here, sig equal to 10 indicates that it is sig user 1. We'll just zoom into the point where the signal delivery happened. You can observe that the signal was delivered at this instant, and during this instant the low priority thread to which the signal was delivered was runnable, and the high priority thread which was running delivered the signal to the low priority thread. Further zoom in, you can observe that the high priority thread generated the signal here, which is indicated by this signal generate, and it also indicates the thread ID 3617, which is the high priority thread 3617 here. So after sending the signal to the low priority thread, the high priority thread simply executes a for loop for some time, which is here, that can be seen here with a small pink colored box. And after the high priority thread stops, the low priority thread again comes into the picture, and the signal is delivered instantaneously. And after the signal is delivered, we print the signal handler gets executed, prints the value, and exits. Now after the low priority thread exits, you can see that the main thread becomes runnable here, and the main thread simply prints the counter variable and it exits. That can be seen here. So that's I would like to thank Dr. Lee for his support and guidance in the embedded systems programming class. I hope you all enjoyed the video. Happy coding, and thank you for watching this video. Bye bye.